following a DC-9 3-mile final.
Left 30, left 345.
1243, runway 3 is left, action position, hold jet traffic, 5.5 mile final.
1243, position, hold 30 left. PSA 6051.
PSA 1651 says the tower, runway 3 is left, cleared, land wind 2804, following a tri-jet.
Life is exciting these days, if you can keep up the pace. Take this place. The people responsible for keeping it running have to make decisions, plans, and schedules in the face of overwhelming amounts of information. The need for quick decision-making often exceeds normal capacity. But, of course, the same is true in manufacturing, administration, any complex enterprise. That's why IntelliCorp is in the knowledge processing business. We produce software that can help experts decide or plan or schedule. For instance, here's the GATES program, produced with IntelliCorp's knowledge engineering environment, the KEE system. GATES is a model for a system that could help ground traffic controllers at airports. It's designed to help them assign airplanes to gates. The controller can choose which aircraft will be assigned next. The system determines and brings up the appropriate terminal for the aircraft by looking at the airline of the aircraft. Then, rules operating behind the scenes automatically select possible gates for the aircraft on the terminal in question, capturing the knowledge a controller would use to make the decision. If the controller wants to know why a certain gate was suggested, the program can explain its suggestions. In this case, it turns out that Gate 7 is a possible gate for Jet 2 because, among other things, it has sufficient capacity to accommodate the number of people coming off that aircraft. The controller can then choose from the possible gates. Assignment is shown on the terminal, and the assignment information panel is cleared for the next plane. Once satisfied, the controller can choose another aircraft for assignment. If the same terminal is appropriate, no change will be made. Again, the preferred gate can be chosen from the possible gates. The program shows the assignment on the display panel for the terminal and then prepares to repeat the choice cycle.
Ladies and gentlemen, this is Captain Riley. Sorry about the delay. At the present time, we're having some trouble with our assigned gate, so we're standing by for a new gate assignment. Shouldn't be long now. While we're waiting, we do ask that for your continued safety, you remain in your seats.
For those passengers awaiting the arrival of Flight 25, we seem to be having some difficulty at this gate. We'll be announcing the new gate in just a moment.
Of course, the best laid plans sometimes go wrong, but that's when programmed aids really show their value. Using the GATES program, a controller can quickly indicate that a gate resource has gone out of service. Using a different set of rules, the program automatically determines that a jetway problem is sufficient to put a gate out of operation. The jet which was assigned to the bad gate will then be top priority in the waiting queue. Reassignment can then be immediate and swift so that delay can be minimized.
The new gate for Flight 25 will be Gate 12.
So, finally, with a minimum of confusion, the travelers arrive at their intended destinations. The problems of information management, decision-making, scheduling, and planning faced by ground traffic controllers are indeed common to many fields. KEE, the knowledge engineering environment, aids in the creation of programs which can be of help. KEE is an integrated set of programming facilities for developing computer-assisted decision-making systems in many application domains. Welcome to the video component of IntelliCorp's self-paced basic training for the KEE system. This videotape consists of 2 parts. In the first part, we'll give an overview of the parts of the KEE system and some basics about use. In the second part, we'll discuss how you can use what you've learned. Several experts from IntelliCorp will discuss some issues in design and implementation before you begin building your own system. We recommend that you view this part of the video before you begin to work on the exercises in the training manual, and then return to view the second part of the tape right after you complete the exercises. But if you wish, you may watch the whole program, then return to it later after you've worked the exercises. Now, let's continue with our discussion of the parts of KEE and how they're used. We like to think of the KEE system as a set of power tools. These tools allow you to quickly build up a model of your domain. To introduce the basic power tools in KEE's toolbox, we'll demonstrate how each one was used in the Gates demo you've just seen. We'll be looking at 3 major aspects of KEE: knowledge representation, interface, and reasoning. Under these broad headings, we'll introduce the basic parts of the KEE system. For advanced KEE users, there are additional tools for extended reasoning and interface design. These are the KEE Pictures graphics package, the KEE World's Multiple Worlds facility, and KEE's Truth Maintenance System. They will be discussed in advanced trainings. You may read about them in your KEE reference manuals. Now then, how is knowledge representation handled in the KEE system? Using units. Units, or frames or objects as they're sometimes called, can be pictured as filing cabinets. Each unit has attributes, places to put information which can be thought of as drawers. They're called slots. This cabinet, for instance, might represent a particular jet. Let's say Jet 1. This drawer contains the capacity of Jet 1, which happens to be 250 people. So, slots can contain information about a unit's attributes or characteristics. If we have one filing cabinet, 1 unit for each jet, then all the information about a given jet is collected handily in one place. This is useful both conceptually and practically. We've built here a model of how one might represent and reason over a sample problem, how ground traffic controllers might assign gates to incoming aircraft based on certain constraints. The current stage of the gate system would be called a pilot demo. It's not a finished prototype, but a system to give a feeling for what's possible. What you see here is a graphic representation of that model called a knowledge base. A knowledge base is a data structure representing knowledge in a particular domain. It's a collection of objects which represent the things in the domain. Our present domain contains various sorts of aircraft, some airport gates and gate agents, and a control tower. And here's the inside of one such object, the Jet 1 unit. The unit slots are visible. Of course, just as a jet is a unit, an airport gate or control tower is a unit as well. Even an intangible thing like a flight plan or a trip could be represented this way. Now that we have several units, we can demonstrate another important use of slots. Slots in one unit can point to other units. Here, it turns out that the assigned aircraft of the Gate 1 unit is the Jet 1 unit. So, in addition to representing attributes of units, slots also give us a way of representing relations between units. There are some other important points to make about the slots or attributes of an object. First, slots can contain behavior in the form of programs. This program in slot capability is the basis for KEE's object-oriented programming. We'll discuss that further along. Second, just as slots contain information as attributes of units, structures called facets contain information about slots. It's like having drawers within drawers. Facets are often used for consistency checking. For instance, a facet called value class can make sure that only appropriate values are permitted to enter slots. Cardinality facets ensure that slots don't get too many values or too few. Several other facets are provided by the system, and users are free to create as many as needed. Perhaps the most important point about slots is that they permit information to be passed from one unit to another by inheritance. Let's see what this means. We've seen that units can represent individual things, but it's often useful to categorize individuals. For instance, these three objects are members of the class of jets. Classes, like the class of jets, can be represented as units, just as individuals can. To help with gate assignment, we want each aircraft to have a capacity slot. So why should you create that slot from scratch in every single plane? It makes more sense to establish the slot once and for all in the airplane's class-level unit. Then, any individual airplane can, as we say, inherit the slot, and the user can specify the capacity for each individual aircraft as appropriate. Now, all airplanes are not equal. There are jets, propeller-driven planes, etc. They're all airplanes, so they can all inherit airplane-like characteristics, like the capacity slot. On the other hand, there are characteristics they don't share. Differences in size, staffing, and runway requirements make it worthwhile to establish subclasses of aircraft, which we see here linked to the aircraft class with solid lines. You'll see later how this distinction can be useful. We've discussed KEE's frame-based representation and the advantages of facets and inheritance. Now, what about interface? We usually think of interface as related to interaction between the end user and the program. But in KEE, there has also been an emphasis on providing a powerful developer interface. For instance, look at the Jet 15 unit, with the classes it belongs to and its slots and slot values. How did the information get there? How can it be changed? One way is through the KEE system's mouse and menu interface. Using this style of interaction, it's easy to create a unit like Jet 4 in the Jets class. To examine the new unit, we can update the knowledge base display. By selecting Display from the left button menu on the Jet 4 unit, we can get a view of the slots automatically created inside. Building and checking on other aspects of frame structure through the mouse and menu interface is just as easy. We can create slots, create subclass links, and so on. But there are other ways to interact with your knowledge base. KEE also has a programmatic interface based on Lisp. This gives us a second way to build or find out about structures. Here, we're using the KEE user function createSlot to make a new slot. We can insert contents into the empty slot using the function putValue. Then we can fetch that same value using the function getValue. A third form of interface is KEE's tell and ask language. As with the programmatic interface, it's straightforward to create a new instance of the class jets. This form of unit creation takes advantage of a special English-like syntax that is more transparent to non-programmers than the use of Lisp functions. Here, we've used the assert function to modify the knowledge base. This time we use tell and ask to set the value of the assigned gate of Jet 6 to Gate 2. Notice that the syntax is different from the syntax used to create a jet. Users often want to retrieve a value from a slot. In this case, you can use tell and ask's asking function. It's called query. As we'll see shortly, tell and ask is the language of KEE's rule system. In fact, an important reason for developing the language was to make rules more readable. A fourth style of interaction, perhaps the most appropriate for end users, makes use of the KEE system's active images. One sort of image, the traffic light, shows the possible values and the actual value of a slot. Here we have an image which lists the possible states of Gate 1, OK or out of service. In this case, the value in the slot is OK. On many kinds of active images, values may be asserted into slots by buttoning on the image. These are actuator images. By clicking on an image, we can easily get access to the unit it represents. Here is Gate 1's status slot. We've only scratched the surface of active images, so before leaving the subject, we'll add a few images to the current passenger number slot of Jet 15. Here, A bar graph actuator and a digi actuator have been attached to this slot. Now we add a third image, a dial. Of course, all these images reflect the same data consistently. Values inserted through the images wind up in the current passenger number slot. Now, let's continue on to the next major heading of our orientation tour, that of rule-based reasoning. How do we determine the possible gates for a given aircraft? How do we know when a given gate should be in or out of service? Knowledge of this kind is sometimes represented in the form of rules. If A, then B. This typical key rule says, take a member of the aircraft class and a member of the gates class. The question marks indicate key variables. If it can't be shown that the gate presently has an assigned aircraft and the gate's status is okay, and the gate can handle enough people for the aircraft in question, then the gate is a possible gate for that aircraft. Note the relation between rules and frame-based representation. For instance, status and possible gate are slots in the relevant gate and aircraft units. Notice also that the tell and ask language is used in rule premises and conclusions. As we've mentioned, rule clarity was a primary reason for the development of tell and ask. The KEE system supports two styles of rule-based reasonings, forward chaining and backward chaining. Backward chaining begins by posing a question. To illustrate, we'll ask what the possible gates of Jet 1 are. Rules in the possible gates rules class will be invoked. Possible gate rule 1, the rule we've already examined, is a member of this class and is found to be applicable. The rule system will automatically try each member of the gates class in turn. At the moment, it's looking at gate 5 behind the scenes. Since gate 1 does not have an assigned aircraft and its status is okay, it only has to be shown that it can hold enough people. Luckily, there's a rule that can prove this, sufficient capacity rule. When the rule system invokes the second rule in the course of trying to verify a premise in a prior rule, we say it's backward chaining. Sufficient capacity rule simply defines sufficient by saying that if the gate's capacity is greater than or equal to the aircraft's capacity, then the gate does indeed have sufficient capacity for the aircraft. Since this is the case for Gate 5, the last premise of our first rule can be verified. Gate 5 is a possible gate of Jet 1. Whereas backward chaining begins by posing a question, forward chaining begins by stating a new fact. The rule system must try to find its consequences. This time, the rules in the Gate Out of Service Rules class will be used. The fact we asserted, the status of Jetway Motor 1 is failed, turns out to match premise of bad Jetway Motor rule. Since all the premises in the rule can be verified, the rule can be applied. Its conclusion becomes known. The status of Jetway 1 is out of service. But this new fact is in turn a premise of Jetway Out of Service rule, which states that when a jetway is out of service, the gate is out of service too. This rule will also be applied. The first rule's conclusion was a premise of the second rule. It is this rule-to-rule linkage that brings about forward chaining. Whether you chain forward or backward, rule-based reasoning has several advantages in KEE. The KEE rule system provides a very flexible control structure. For example, interleaving forward and backward reasoning is easy. Users find rules more readable than code, and there are extensive debugging aids for the developer. You'll recall that one of the crucial features of slots is their ability to contain programs. In object-oriented programming, such programs represent the behaviors of the objects which contain them. Programs in slots are called methods. Here's a method in a slot of Jet 16. A method knows what unit it's in. Thus, it's possible to use the identical assign self to gate program in Jet 1, Jet 2, or any other jet. To see how methods are activated, let's rerun the assignment of Jet 1 to a gate. The most direct way is to issue the activation command right from the slot menu. Once any necessary input has been supplied, the method proceeds. Rather than activate each method by hand, we can let methods activate other methods. In the Gates program, for instance, we have a tower unit that notifies Jet 1 and other aircraft of their gate assignments. When the user selects a gate for the current aircraft, the method Notify Aircraft of Gate Assignment is activated. It sends a message to the current aircraft to assign itself to the gate that was just chosen. When one unit calls another in this way, we say it sends it a message. By the way, how did each airplane get an assigned self to gate method? The same way it got its other slots, by inheritance. The method slot passed all the way down the class hierarchy till it arrived at Jet 1. The important point is that units inherit behaviors the same way they inherit other attributes. So the object-oriented programming style is a natural extension of frame-based representation. There's a bit more to say on the benefits of object-oriented design. Notice that since the tower and Jet 1 each have their own procedures, they're quite self-contained. In the gate assignment task, the tower decides what the assignment should be by looking at its current aircraft for assignment slot. The airplane acknowledges and completes the assignment. As far as each unit is concerned, the other one is a black box. This clear separation of duties makes for a modular and clean programming style. This modularity makes it possible to distribute intelligence in an intuitive way. For instance, consider the task of pre-takeoff checkout of aircraft. If a single program did the actual check, it might have to know the exact procedures for many different kinds of aircraft. To summarize, in object-oriented programming, objects, that is, units, can contain method slots representing behavior as well as slots representing attributes and relations. Just like other slots, method slots are passed down the unit hierarchy. This extends the benefits of frame-based representation into the area of programming. Objects activate each other's programs by sending messages. This lets you distribute the processing load and put the knowledge where it makes most sense. And objects are relatively self-sufficient, which aids modularity. We've seen two ways of activating methods. Users can activate them by mousing on them, or methods can invoke other methods by sending them messages. Often, it's desirable to have a method watch out for certain events and activate automatically as soon as the event takes place. For instance, in the Gates program, if a jetway goes out of service, then the Gates image should be changed so the user will know that it's out of service. This is a job for the KEE system's active values. The active value is itself a unit, a kind of guard unit assigned to watch a slot. Such guard units contain methods themselves. These are activated automatically when the watched-for events occur. In our example, if a gate becomes unassignable due to an inoperative jetway, the active value automatically awakens and begins reasoning about the consequences. Active values can be inherited. For example, an active value unit may be attached to the jetway's class and will then be passed to each individual jetway for guard duty. Since active values are independent units, they're modular. For instance, we've used the same active value unit for the behavior of jetways as for the behavior of agents. Such modular code reuse is one of the great benefits of working within an object-oriented system. KEE's active values are well integrated with frame-based representation and object-oriented programming. In the first place, any active value is itself a unit. An active value unit contains methods which implement its watching behavior. These are inherited from the class of active values. Active values not only are units, they watch slots in other units. This ability to create reusable, automatic behaviors in an object-oriented programming environment allows the designer to integrate actions and reasoning into effective simulations in many domains. You've now seen a brief discussion of the KEE system's basic parts. You've seen how representation, interface, and reasoning are interwoven to provide an integrated environment for applications development. But this is only the beginning, and we've only covered each topic very lightly. Before going on to the second half of this presentation, do the exercises in the training manual. Make use of the reference manuals as you do. Then, when you're done with the exercises, you'll be ready for the last segment of this video.